welcome to your final lesson on limits, which is the formal definition of a limit. Please do note that this is not going to be assessed in class. It's not going to show up on any tests or any formative assessments. It's simply to give you a bit of a leg up as you head into your university calculus classes, because they will probably start here. And the formal definition of a limit, well, there's a reason that we didn't give the definition at the beginning. It's a bit complicated to understand, but understanding it gives you some insight into what the limit actually means. So let's start with the definition and then we'll unpack it a bit. So the definition of a limit. Okay, so let f of x be a function defined on an open interval containing the point x equals that's not properly spelled, containing the point C, except possibly at C. So the value of the function, it doesn't necessarily have to be defined at that point. But it needs to be defined on the rest of some open interval containing C. And let L be a real number. You might see that written as just let L element of R. That means the same thing. Okay. The statement the limit as x approaches C of f of x equals L. So we're approaching a point, we have an L, C is our x value, L is the y value that we are approaching but not necessarily arriving at. So what this means we are going to write this symbolically, but I will unpack the meaning of each of the symbols. So this means that for all epsilon greater than 0, so this is for all, remember this is a good symbol to know as your professors will use it without explaining it, there exists a delta greater than 0. Such that if the difference between x and c, or the distance between x and c, is greater than 0 and less than delta, or the absolute value of x minus c is between 0 and delta, we are within delta of c, then the absolute value of f of x minus L is less than epsilon. So for any epsilon we pick, there's some delta, so that as long as we're within delta of C, our y values have to be within epsilon of L. And that's true for all epsilon. Wow, what a statement. You can probably tell why we didn't start with that in Calculus 12. So let's unpack it graphically, because that can be a little easier to understand what it's saying. Okay, so let's see. Okay, and one thing we may want to recall as we unpack this graphically is if, say, we have the absolute value of x minus c is less than delta, what this means is that if we're on a number line and we have c, that we are between c plus delta and c minus delta. And have a look back at that section in your very, very first unit if you must. And so if it's between 0 and delta, it means we don't include c. So having a look at this definition graphically. So let's go through. So we have our function f of x. So we've defined a function f of x. We're going to make it a certain particular way so that we can really unpack this properly. Okay, so let's pick a c value. Okay, so let's say this is x equals c. As we get closer and closer to c, we know just our sort of use definition of a limit is the number that we're getting closer and closer to from both sides in the y as we get closer and closer to a particular point in the x. So that's our L. So back to the definition. For all epsilon greater than 0, there exists a delta. So for all epsilon means let's pick some specific epsilon. This statement doesn't have to be true for just this epsilon. It needs to be true for any epsilon. But we're going to pick one just so we can kind of illustrate what it looks like when we do it to a graph. So we're looking at this little distance of epsilon because we need to be epsilon away on either side. So we have L plus epsilon and L minus epsilon. And so what that does is that gives us a little range from here at L minus epsilon to L plus epsilon that we have to stay within. So that gives us a little kind of green range of our y values. And what we want to do now, so there exists a delta, so that as long as we are within delta from C, then our y values will be within epsilon of L. So we want to pick a delta so that as long as we stay within delta of C, we're only going to be within that green region of the graph where the y values are within epsilon of L. So if we look here, there's sort of two possibilities. This is where the green range starts, and this is where the green range kind of ends. So we really are looking for the smaller of those two possibilities because we're missing some of that green range. So let's make this right here. We can see that this distance on this side is clearly shorter. So let's make this here sort of C plus delta. Could I pick a smaller delta? Could I have made delta like right here instead? Absolutely. Often we're looking for sort of what's the biggest possible delta for the epsilon we have, or even can we find the biggest possible delta given a certain epsilon. So here we have C and C plus delta. And so on the other side, we're going to try to make about the same distance and get a C minus delta. And we can see that our y values here are clearly within that sort of green range. They have to be right in between there. So all of our y values in this delta, if we look at, we're within delta of C, all of our y values are really clearly within the green. And that's what we want. So what the definition is, so this is an illustration of one epsilon and finding one delta that goes along with that epsilon. The definition of a limit says not only does this work for one epsilon, it has to work for any epsilon you pick. So whatever epsilon you pick, you have to be able to find a delta so that when you are within delta from C in the x, you will always be within epsilon of L from the y. Okay, so it's a little recursive because you kind of start with epsilon, find a delta. Being within the delta means something about the epsilon. So it's kind of a little bit of a back and forth. Okay, so when we're trying to prove or define a limit at a certain place and prove something about limits, we need to prove that given some epsilon greater than 0, there has to exist, in the y's, there has to exist some delta greater than 0 for the x's. And so we're going to look at a couple of algebraic proofs of that. So we're going to prove that the limit as x approaches 1 of 3x times x minus 1 over x minus 1 equals 3. Okay. So this means we need to prove that given an arbitrary epsilon greater than 0, there exists a delta greater than 0 that satisfies the requirements. So the easiest way to do this is to find that delta in terms of epsilon. So for example, if we pick an epsilon, then that epsilon divided by 10 will give us a delta that always works. So let's check it out for this particular problem. Okay. So what we're going to start with, okay, is let's have 3x times x minus 1 over x minus 1 minus 3. Let's say that we are within this epsilon greater than 0. So we're going to choose an epsilon. We're just going to call it epsilon because we're given an arbitrary epsilon greater than 0. So let's show that there exists a delta that satisfies our requirements. Okay? So let's simplify here. We can simplify and cross these out. So we get the absolute value of 3x minus 3 has to be less than epsilon. You can even factor out a 3. 3 times the absolute value of x minus 1 is less than epsilon. And we get x minus 1, absolute value of x minus 1 is less than epsilon over 3. Well, why is this helpful? Well, what happens is we're looking at, so we want to show that if x minus c is less than delta, 1 is our c. So if the absolute value of x minus 1 is less than epsilon over 3, so this is our delta. This is our c, because we are looking at the limit as, if you see here, we have the limit as x approaches 1, so 1 has to be our c. So the absolute value of x minus 1 is less than epsilon over 3. Okay. Then we know that the absolute value of f of x minus L is less than epsilon. Okay, so we have that this is equal to 3. This is, as we look through the proof, this 3, that's where this 3 came from. That was our L from our definition. So we have our L, we have our epsilon, and we have our f of x right here. So this right here, which I'll do, is our f of x. So we took an epsilon greater than 0. We proved that there exists a delta greater than 0 by finding that delta in terms of epsilon. Okay? All right. So let's try. Now we have to show that our delta actually works. So we have our if, that this is true. Epsilon is less than epsilon over 3. So we have to work our way backwards. So we can multiply both sides by 3. So then 3 times the absolute value of x minus 1 is less than epsilon. So the absolute value of 3x minus 3 is less than epsilon. And if we multiply the 3x times x minus 1 over x minus 1, so 3x times x minus 1 over x minus 1 minus 3. The absolute value is less than epsilon. So if we pick that epsilon, we will always end up with our f of x minus L less than epsilon. It's a bit of a recursive process. You have to go through, find your delta, and then you have to go back and sort of work backwards again to show that your delta actually works for all epsilon. Okay. So like I said, this is not, I have a couple more videos for you to watch that were not made by me, and I will post a couple of problems if you would like to try them in OneNote from your textbook as suggested exercises. They are not going to be collected. It is up to you if you want to explore this a bit more on your own.